Okay, let's get started. I have this thing on. Yeah. We have talked about stretching things and deforming things. We're going to spend the last few hours of this course talking about breaking things, which is a subject that I've been fascinated with since I was about 6 weeks old. We begin with breaking things at the ultimate tensile strength. That is the failure of materials of plastic instability. We've already described how this happens. If you take a sample in, for example, a tensile test and stretch it, you'll get elastic deformation, followed by stable plastic deformation as the sample elongates but retains a constant geometry until finally we reach the ultimate tensile strength. Now, if we're doing this test under load control, if what we're controlling is the stress, then at this point the sample will break because that's the highest load it can control. If we're doing this under displacement control, the deformation will continue on a bit longer. And what will happen is that the plastic deformation will concentrate, the sample will form a neck, and the engineering stress will go down as the strain increases until finally the sample breaks. Of course, in the context of the true stress, that's not what's happening at all. Because of this necking phenomenon, the cross-sectional area here in the neck is getting smaller and smaller and smaller. So the true stress is going up, and in the true stress strain curve, you don't see this maximum or this ultimate tensile strength. So what's happening here is plastic instability is leading to fracture. Now, there's kind of a fairly simple theory of how this plastic instability develops and when it occurs, which has the incidental property of telling us how to figure out where the ultimate tensile strength is from the true stress, true strain curve. Suppose we have a sample, and suppose it begins to deform plastically. Now, even though the sample overall is deforming uniformly, you've already seen that the incremental deformations are all local. What happens to the specimen is that when an element of plastic deformation happens, we get a little strain here, which will cause the material to deform locally. In fact, that little strain will be normally at 45 degrees to the axis of the bar, but I've drawn it this way because it's easier to visualize and to calculate. One of two things will then happen once that little increment of strain forms. Think about the consequence of that. There are two consequences of this little increment of strain. One is that because the strain happens, the material gets stronger, because the material is always work hardening or getting stronger as we continue to strain it. The other thing that is happening is that the stress that's applied to this little region is getting larger, because the region now has a smaller area. So it's seeing higher stress, the stress is going up, but it's also getting stronger. If the increase in strength is enough to overcome the increase in stress, then the material's not going to deform anymore right there. That material is now the hardest part in the bar, and the next element of deformation will be somewhere else. And in this way, the plastic deformation works its way up and down the bar. Every time a little increment deforms, it gets stronger, so it stops deforming. However, if we get to a point such that the increment in strength due to work hardening is not enough to overcome the increase in stress, then the deformation there will not stop. It will keep on going. I'll get more and more deformation right there because this is now the weakest part of the whole bar, and as a consequence, it will neck down in failure. So what necking is all about is this transition from stable to unstable plastic deformation. Before we get to necking, what's happening is that every time there is an increment of plastic strain in the bar, that plastic strain hardens the bar, so that little local region stops deforming. The deformation goes somewhere else. And so it slowly but surely works its way up and down the bar. When we hit the instability, what happens is once that deformation happens, its increase in strength is not enough to overcome the increase in stress. So the deformation concentrates there. We get a necking, stress increases without bound until finally the material fractures. Now, what is the mathematical criterion that we govern that? Something called the Considere criterion. It's fairly easy to derive. I'll just trace through it. Suppose we have a little increment in plastic deformation right there. I've idealized it in this picture, but it's pretty much what's happening. What happens there is this little region marked in red is strained, so it's increasing in strength. It's also decreased in cross-sectional area, so the stress applied to it has gone up. So let's compare those two. The increase in strength, d sigma, is d sigma d epsilon, where d sigma d epsilon is the work hardening rate. D epsilon is the strain. The increase in stress, well, the stress is P over A. dP over A, P is constant, is a given, so dP over A is P over A minus dA over A, which is just sigma d epsilon, where epsilon is the true strain. So the increase in strength is d sigma d epsilon, The increase in stress is sigma d epsilon. If the increase in strength is greater than the increase in stress, this little area stops deforming. We have stable plastic deformation. If, on the other hand, the increase in strength is less than the increase in stress, we go unstable. So the transition to unstable plastic deformation is hit when these two terms are equal. That is when d sigma d epsilon is equal to sigma. This is called the Considere criterion. It says when the work hardening rate is equal to the applied stress, then plastic deformation becomes unstable, the sample necks, and it fractures. So this is the criterion that gives us the ultimate tensile strength, now expressed in the true stress and true strain. And the way we can find the ultimate tensile strength from a true stress, true strain curve is just take the slope of that curve, which is the work hardening rate, d sigma d epsilon. And what I've done here is to plot both sigma versus epsilon and theta, d sigma d epsilon versus epsilon. As we strain the sample, the strength goes up, elastic and then plastic like that. The work hardening rate comes down. We can go into the theory of that, but that's a bit beyond this course. Just accept the fact that the hardening rate does decrease monotonically. So we finally going to get to a point right here where the two become equal. That's where the plastic instability sets in. That's where the sample necks. That's the ultimate tensile strength in true stress, true strain coordinates. So that's the reason we get fracture in a tensile test. We strain the sample until the work hardening rate falls below the applied stress. At that point, plastic deformation becomes unstable. We get necking. Necking leads to fracture. And that's plastic deformation. So this just shows you that everything works out. The ultimate tensile strength, d sigma d epsilon equals sigma, or dsde is equal to 0. If I express the engineering stress and the engineering strain in terms of the true stress and strain using the equations that we've derived before, and just perform that differentiation, you see that dsde is e to the 2 epsilon power d sigma d epsilon minus sigma. When the Considere criterion is satisfied, the SDE is equal to 0. The engineering stress strain curve is at its maximum right there. So on the engineering stress strain curve, we get plastic instability at the peak in the curve. On the true stress strain curve, we need two curves. We need both the stress and the work hardening rate, and we get plastic instability when the two hit. Now, I should warn you here, well, it's not that important, but as peripheral information. In deriving this Considere criterion, we did assume that the area decreased in an equiax manner, and that's true for a cylindrical bar or a bar that's equiax in its various dimensions. Many tensile tests are also done in thin sheet specimens. And in a thin sheet specimen, you're only really thinning in one direction rather than in two. And that has the consequence that in a thin sheet, the instability happens when the work hardening rate drops to sigma over 2 rather than sigma. So the criterion for instability, the mathematical criterion, is a bit sensitive to the geometry of the specimen, but this is a good rule. It's going to be pretty close to right always, and you see it. So that's plastic instability. One of the interesting things I told you earlier and showed you some data, this happens to be in aluminum, but any structural material will show you the same thing, is that when you go down to small grain sizes, the strength goes up, but the ductility goes down. In fact, the ductility can virtually vanish. You might say, why does something like that happen? Well, what turns out to happen is the following. I'm going to make an assumption here that isn't quite right, but it's close enough to being right that it's good for illustrative purposes. Let me assume that the work hardening rate, which has to do with the multiplication and the interactions of the dislocations, let me assume that that doesn't depend much on the grain size. It does, but it's not nearly as strongly dependent as the strength is. So let me just take a plot here and show you what happens when I start decreasing the grain size. As I decrease the grain size, the strength gets higher. That means the true stress, true strain curve is moving up like this. But if the work hardening curve were to stay the same, and to a first approximation it does, you see what happens. The strain at which plastic instability intrudes starts moving back and back and back until finally the sample becomes effectively brittle. And you can kind of see that here. This is the yield strength. This is the ultimate tensile strength. This curve actually comes from a much more sophisticated model. As a function of the grain size, as the grain size gets very small, the yield strength increases. The ultimate tensile strength also increases, but not nearly as fast, so the two eventually coincide, and the material is effectively brittle. And you see that happening here. In the actual data, here's your ultimate tensile strength, and it's becoming close to zero at the end of the elastic region. And that's because when you do things like refining the grain size, you are boosting the strength without having a concomitant effect on the work hardening. To actually get materials that are both strong and have some elongation to them, we need alternate mechanisms of work hardening. How we do that's a bit beyond the scope of this course, but one way to do it is I mentioned briefly transformation-induced plasticity, where you use a phase transformation, a structural transformation, to get yourself some kind of free strain. And that, in fact, is an effective method for getting the elongation up. But in the natural behavior of things, as the strength goes up, the elongation goes down, so we have a trade-off between strength and ductility. And a lot of the development of structural materials is involved in finding ways to cheat Mother Nature and fight that trade-off. We do it with things like transformation-induced plasticity. Okay, now let me just go more specifically to fracture. There are really three different modes of, when we talk about breaking things, there are three basic ways that things break mechanically. You can also rust them away or you can wear them away, but in just under load, there are three ways things can break. There can be an elastic instability, buckling or flutter. What happens in elastic instability, the classic case is where I just take a column and I push down on it. The column bows out. As the column bows out, because the force the column can resist the load on goes along the axis of the column, you get a bigger and bigger angle between the force you're pushing down on the column and the angle at which the column is pushing back. You finally get to a point where this bowing out causes a situation in which the column can no longer resist this load. And it collapses. You form a hinge here, and it just folds over. A dent in a car is a classic example. You know the hinge along the edge of the dent. That's an elastic instability. A similar elastic instability, and a much more spectacular one, is flutter, where you have something like, unfortunately, the wing of an airplane. It's happened before. I've investigated it before, where you begin to see it bouncing up and down. If you're flying around, look out the window. The wing of the airplane is doing this. Well, now let's suppose that in doing this, you happen to hit a natural frequency of the wing. So every time you push on it, it gets bigger and bigger. In that case, you can knock the wing off. The classic flutter example, I'll show you a case in a minute, but one of the classic ones was the French army marching into Italy with their hut to across a bridge, and they hit the natural frequency of the old stone bridge, and a piece of Napoleon's army went into a gorge in the Alps. Elastic instability. Plastic instability we just talked about. Plastic instability causes a neck. Ultimate tensile strength, this thing breaks. The final thing, which is in many ways is the most invidious because it can be so totally unexpected, is crack instability or fracture. In this case, what happens is you have a crack in the material. You may not know it's there. You put a load on the material. The load may be well below the yield strength of the material, but that load is intensified at the tip of the crack, as we'll discuss in just a few minutes. And because of that intensification of the stress, you may create a situation in which that crack goes unstable, propagates through the material, and bang, you've broken it. And that can be such a threatening thing because you don't necessarily know the crack is there. As we'll see, there are mechanisms in which cracks can appear in the material during service. Fatigue, stress corrosion, cracking. And so you can be operating something and it's operating fine, everything is great, all of a sudden it breaks. With no warning at all and under no unusual load at all. And so this is a very important kind of failure to understand. Just for example, this is the Tacoma Narrows Bridge. This may be the most, this is the usual spectacular example of a flutter failure. I dug through the files. I've got the film on this somewhere. If you just go online and Google the Tacoma Narrows Bridge, you can actually get the YouTube video of this happening. This thing had been, what most people don't know is that the principal loads on a bridge or building are actually wind loads. The wind load on a bridge is much more threatening in terms of design than usually the weight of the cars or such things going across it. Not that you can't overload a bridge. We almost overloaded the Golden Gate Bridge some years ago when they decided to open the bridge and let people onto the bridge. And suddenly to their shock, they discovered that a mass of people weighs an awful lot more than the normal traffic of cars. And the bridge started bowing. And in complete panic, they set off all the sirens, had to get everybody off the bridge because it was in danger of coming down. And they haven't opened it up since. So yeah, this was celebrating the 50th anniversary of the Golden Gate Bridge. Seemed like a great idea at the time. We just let everybody walk out on the bridge and we shut down traffic. But nobody sat back and calculate that people standing shoulder to shoulder weigh more than cars lined up one after the other. In fact, I wouldn't have thought that, but they do. And they also had a problem with the Golden Gate Bridge. Anyway, the regional threatening load was wind load. And what happened to the Tacoma Narrows Bridge? Well, it was the Narrows. And Narrows have a tendency to be windy. And they built this bridge, and suddenly they started finding it going into very, very large vibrations. And so they realized they had a problem, that this thing was in danger of fluttering itself to death. And sure enough, one day this started getting really bad. They shut the bridge down, although there's still a car on it up here, as you can see. Who that guy was and what happened to him, I don't know. But it started oscillating wildly, and there's a movie that you can watch showing these wild oscillations. Someone actually filmed it. And then it just collapsed, came down, and that was the end of the Tacoma Narrows Bridge when they rebuilt it and did a little better. This used to be much more of a problem than it is now. I think I mentioned the Lockheed Electra had a big problem with wing instability when it first came in, the first private jet plane. The reason was that in order to design around this kind of problem, you've got to be able to identify the natural frequencies of your structures. Now, this can be an enormously complicated thing. If you're in mechanical engineering, maybe study vibration a little bit. You not only have to worry about the primary vibrational modes, you have to worry about all the harmonics of the vibrational modes. And because instability is an instability. And if you excite the sixth harmonic, which you may not even see in normal operation, you excite that thing to instability, you've just lost your part. In fact, in a typical Continental engine, which is a problem I'm going to worry about in a moment, it is in fact the sixth harmonic of the vibration of the crankshaft that is the most threatening as far as possible destruction of the crankshaft. That's what you have to worry about. Hard even to measure that thing, but it's what you have to worry about. Well, until fairly recently, vibrational analysis was enormously difficult, simply because most of the structures we have to worry about are not simple structures. If this bridge were in fact a simple beam, then even in the 1940s, they could have done a pretty good job of analyzing its harmonic vibration and designing around any problems. But look at it, it's not just a beam. You've got these columns sticking up, you've got the behavior of these cables, these wires, all these things interact. And the natural frequencies will be joint natural frequencies of all these different components. So while you can kind of approximate, or they could even in those days, kind of approximate the vibrations of a bridge from building simple models and analyzing those, it was really tough to get hold of the real models. And as a consequence, we had periodic. It was always dangerous to fly a new airplane because you just didn't know if they'd caught the harmonics or not. In the Lockheed Electra, it was the wing. In the British Comet, it was a pulse mode of the body itself that caused a number of cracks. In fact, destroyed the British aerospace industry for a while. That again was a vibrational instability. Now we have these big, fancy, powerful computers, and you can literally do things like an entire automobile in finite element analysis. You can take your entire automobile, run it into a wall, and analyze the whole thing on the computer. So they're very sophisticated programs these days. However, the issue of vibration is so complicated that it still remains possible that in a new machine somebody will miss something, and there will be some obscure harmonic out there that gets excited under some obscure load, and they just never looked at that in the computer. You know?
How easy is it to fix post-production? Say,
If you know how to, what's happening is very easy. You just put dampers of one kind or another on. In the case of a crankshaft in an engine, say an aircraft engine, there are little sets of counterweights. In fact, in some of the engines, in addition to little counterweights, they'll have a viscous damper, which is a disc inside a viscous fluid that turns around. So you just put things in. You see, the thing about natural vibrations is that unless you really blew your design, you are talking about instabilities in some harmonic, some complex vibration, which in ordinary circumstances you'd never see. If you build an engine and you test it and it's rattling all over the place, you say, hey, I've got a problem. What you've got to worry about is you build an engine and you test it, and the rattle is a natural displacement of 1/10 of a millimeter. You're never going to see it, never going to notice it, you nobody knows it's there until the right impulse comes along, which is just dead on the natural frequency of that 1/10 of a millimeter, and suddenly it becomes half a foot, and you mix my units, and there goes your engine. So that's the reason it's such a difficult thing to handle. But because the ones that you miss are so small, if you know they're there, it's very easy to fix them. You just put on a counterweight, change your weight distribution slightly, and you'll change that mode, and then it goes away. But it's always a serious risk. You can fail some pretty big things. Yeah.
So you have one mode, then you change the mode, you have to worry about that.
Oh, sure, you got to worry about introducing instabilities, yeah. But for various reasons, yeah, you have to worry about that. But remember that if you have a vibrational mode that's going to pick up some obscure vibrational mode and destroy an engine or some other piece, then that's a combination of two things. It's a natural frequency of your assembly, and it's also your power plant is somehow producing that frequency too. So the two things have to kind of match together. So if you move the natural frequency, the chance that you will move the natural frequency to some other frequency that the power plant is producing is not very high. So if you can find out where your problems are, they're usually not that difficult to solve. It's the first failure you got to worry about, or the first series of failures while you're trying to figure out what the problem was, which is what happened in both the Comet and the Lockheed Electra. Plastic instability, you see those all over the place. The classic case of plastic instability explosions. This happened to be a propane tank that blew up, caused a fire. One of the interesting things about explosions like this, I don't want to kill too much time today, but there are two kinds of explosions. It's very, very important to keep in mind. There are hydrostatic explosions and there are pneumatic explosions. This, by looking at it, one can immediately tell it's a hydrostatic explosion. This thing happened because the tank was overfilled with propane. Turned out there's a safety valve in the tank, the guy welded it shut because it was causing problems. And then overfilled with propane on a hot day, so liquid expanded, boom, there goes the tank. You know this was caused by an expansion of the liquid because you have this relatively small fisheye failure. You have a liquid, you expand it out so that the force gets big enough to exceed the ultimate tensile strength in the tank, usually some weld in the tank, and it's going to blow up. But the minute it fractures, the minute the volume has a chance to increase, the pressure goes away because the compressibility of the liquid, even propane, is pretty small. The other case that happens that leads to some really spectacular failures is when instead of a liquid, we've got a gas in here. That's a pneumatic failure. Gas, PV equals RT. So when you increase the volume, the pressure goes down, but it doesn't go down that quickly. So you start a crack like this, and it only partially relieves the pressure. So it keeps going, and keeps going, and keeps going. And that leads to things like failures they've had in gas pipelines running across the desert that run for miles before they've stopped. And it just, that can happen. So these kinds of failures, explosions, tank explosions and such things, are examples of getting yourself into a situation where the pressure causes the stress in the wall to exceed the ultimate tensile strength. These are plastic instability failures. Of course, you can also get tank failures from true fracture, but this one was plastic instability. This is a broken crankshaft in I think this was a Cessna 210, I think. Anyway, this was the crankshaft in the engine. It's broken. This was a crack that grew, in fact, in fatigue, which we'll talk about later. But you see this nice, flat, sudden fracture, and this caused a loss of this aircraft. In fact, this crack grew from pre-existing cracks that you can see around here. These are called ladder cracks, and at time next time I'll tell you where they come from. Fracture. So how does fracture happen? We've already talked about elastic instability, ultimate tensile strength. Interestingly, the history of this is not that long. This whole subject of fracture mechanics, which I'm going to tell you about, and will seem to be pretty straightforward, I was not taught. At MIT, when I was a graduate student, there was a single place on campus that taught this subject. In fact, it only came into being in the late 1950s. And the reason has to do with Henry Kaiser in Richmond, California, where they were, during the Second World War, they built an assembly line